Hi everybody, and welcome to our acid-base notes part 3. And we're going to start off with a little warm-up question here that's going to hopefully review everything we've done so far. All right, so what is the hydroxide ion concentration of a 0.45 molar nitric acid solution? So now I'm not going to just be giving you the H plus or the OH minus. I'm going to be giving you an actual acid or a base to deal with. When this happens, the first question you have to ask yourself is, all right, what is this acid? Is this a strong or a weak acid? Well, in the case of nitric acid, HNO3, that is a strong acid. All right, strong acids ionize completely. So let's see, what does that mean? Well, I'm telling you that the concentration of this acid is 0.45 molar. Well, now let's break this up into water, and it's going to break up into H plus NO3 minus. Well, it's going to ionize completely. So that means for every one HNO3, we will get one H plus. Or in our case, for every 0.45 HNO3, we will get 0.45 molar H plus. All right, great. Well, if we know that the hydrogen ion concentration is 0.45 molar, remember we can use Kw as a nice quick way. 1 times 10 to the negative 14th is equal to 0.45 times whatever your hydroxide is. Because remember, Kw is, all right, Kw, just to remind you, Kw is equal to your hydrogen ion, all right, hydrogen ion times your hydroxide ion. And when you solve for that, you get a hydroxide ion concentration of about 2.2 times 10 to the negative 14th molar. Okay, great. All right. Let's look at letter B. Letter B, you have a little bit more work to do. All right, so for B, what is the pH of a 0.025 molar barium hydroxide solution? All right, so again, barium hydroxide, all right, is a strong base, which means it's going to ionize completely. So let's look at barium hydroxide. So BaOH2. All right, and that's going to break up into barium 2 plus 2 hydroxide. So now we have to be careful. The barium hydroxide is 0.025. Well, for every 1 barium hydroxide, I have 2 hydroxides. So I have to multiply that 0.025 by 2, which is going to give me 0.05 molar. All right, so if I know my hydroxide ion is 0.05 molar, okay, I can easily find, remember, my POH, because I'm going to go negative log of 0.05, which gives me 1.30. So my POH is 1.30. Then I'm going to go 14 minus 1.30. All right, 14 minus 1.3. And that's going to give me a pH of 12.7. Okay, so this is a great example of kind of how we've used everything that we have learned so far. All right, so these two examples, A and B, both dealt with strong acids and bases. Today, we're going to be focused on weak acids and bases. Weak acids and bases do not ionize completely. All right, so while strong ionize completely, weak acids and bases do not. Instead, they form an equilibrium situation. All right, because of that, we have what is known as the acid dissociation constant. It's only used for weak acids, and it is very, very similar to our KEQ. So let's take a look. We're going to just use, anytime you see HX, that's just kind of a generic weak acid. And it's going to be in a system of it's going to break up into H plus X minus. But unlike our strong acids and bases, most of it is actually going to stay as HX. All right, only a little bit of it is going to ionize. So again, we get this equilibrium system. So we're going to write Ka just like we wrote KEQ. So my products go on the top, H plus, X minus, over your original acid, okay, on the bottom, because again, this is going to be an equilibrium system. Okay, all right, so let's see this in action. All right, we're going to go right into some examples. So, example A, you have a 0.01 molar solution of ethanoic acid. All right, is only partially ionized because it is a weak acid. The hydrogen ion is 1.34 times 10 to the negative third. What is the Ka of the ethanoic acid? All right, so first off, what you're going to do, step one, write the dissociation equation. All right, so this is going to be nice and easy. Don't overthink this, even though you're going to sometimes get what looks like complicated acids. They're not, all right? Just take this hydrogen, right? So we're breaking up into H plus. Just take that hydrogen off, H plus, and then write the rest of it as the negative ion. That's all you have to do. And remember, this is an equilibrium system. You're going to write your Ka expression. So Ka is going to be equal to hydrogen ion, your products, okay, over your reactant, over your original acid. Okay. You're then going to solve using an ice chart. Trust me, this is definitely the way to do it. It's going to help. Okay, so we're going to start by writing all of our components again. So our original acid, then your hydrogen ion. Remember, it's concentrations of these. And then don't forget about the negative ion that is also part of it. All right, initial change equilibrium. Initially, the concentration of your acid is 0.01. All right, because I have a 0.01 molar solution of my acid. Initially, remember, before it breaks up, you don't have any of those ions. Okay. Once it is ionized, the hydrogen ion is 1.34 times 10 to the negative third. All right, so what that means is that the change is that hydrogen is plus 1.34 times 10 to the negative third. Whatever hydrogen is, your acetate, your negative ion is going to be. So plus 1.34 times 10 to the negative third. Where did this come from? Minus 1.34 times 10 to the negative third. This is just like using that X when we were doing that in the ice charts in the last unit. All right, so at equilibrium, I'm 0.01 minus 1.34 times 10 to the negative third. And then this is just simply 1.34 times 10 to the negative third and 1.34 times 10 to the negative third. You're now going to plug these numbers into this Ka expression. All right, so Ka is going to equal 1.34 times 10 to the negative third squared, because it's H plus times the negative ion, over whatever 0.01 minus 1.34 times 10 to the negative third is. All right, take a moment, put that into your calculator, and I end up getting Ka is equal to about 2.1 times 10 to the negative fourth. All right, there we go. Okay, so let's take a look at another one that is going to be a little bit more of a classic. All right, A. Oops, here we go. So here we go. Methanoic acid, which is right here, has a Ka of 1.8 times 10 to the negative fourth. Calculate the hydrogen ion, the pH, and the percent ionization of a 0.2 molar solution. All right, so this is going to be a little bit more of a classic ice problem. So let's take a look and see what we do with this. All right, so step one, dissociation equation. That's always going to be what happens. Okay. Now, in this case, you could actually take off either hydrogen. It's the front one that we typically take off. All right, so H plus plus COOH minus. There we go. We have that just like we did before. We're going to write our Ka expression. No difference. Ka is going to be H plus. Feel free to pause and try this on your own if you'd like. Great. I'm going to set up my ice chart. That should have been here as step 3. All right, so step 3 is going to be your ice. I, C, E. Then I'm going to go my acid. H plus, COOH minus. Okay, so regular old ice chart. All right, so here we go. Calculate all of these things if you have a 0.2 molar solution. So that means I am starting with 0.2 molar of my methanoic acid. I don't have any of my ions to begin with. Now, in this case, I've given you the Ka, but I haven't given you any information as to what these ions are at equilibrium. So that means this is a classic ice problem. So our acid is going to lose a certain amount. We're not sure what that amount's going to be, so we're going to call it X. All right, whatever the acid loses, the ions will gain, and these both have coefficients of 1. All right, so plus X, okay, at equilibrium, this is 0.2 minus X, X, and X. Fantastic. I'm now going to take this and I'm going to plug it back in to my Ka expression. All right, I've told you that the Ka is 1.8 times 10 to the negative 4th. And so that's going to equal X squared over 0.2 minus X. All right, so here's a little shortcut that we're going to be able to take, and you're going to be able to take this for all of the problems that we're going to have in this unit. All right, we know that methanoic acid is a weak acid. Its Ka is a pretty small number. So what that means is that this hydrogen ion concentration is going to be pretty low. That X is going to be a small number. If we subtract that really small number from 0.2, chances are your number is still going to be pretty close to 0.2. All right, so think about it. I don't know what it is, but let's say it's like 0.0005. If you go 0.2 minus 0.0005, it's still going to be pretty much 0.2. So what we're going to do is we're going to actually just take this away. So we're going to take this away because it's going to be so small. Now, this is a shortcut. We are allowed to do this. If you are to go on in chemistry, there's some rules as far as when you can and cannot use this shortcut. But for you guys, we're going to be able to do this. And this is going to make our math much easier. All right. Because again, it makes us not have to use the quadratic equation. So now, because we've just taken that X away, that minus X away, this is just 0.2 in the bottom. So now we're going to go ahead and solve for X. So you're going to multiply each side by 0.2. Then take the square root, all right, and you're going to find that X is equal to 0.006, okay? All right, it's now that we know X, it's time to answer some of these questions. Again, we've done tons of work. We haven't answered any questions yet. So our first one, calculate the hydrogen ion. Well, my hydrogen ion is X. So hydrogen ion is equal to 0.006 molar, okay? Don't worry that it's only one significant figure. We're not going to worry about that right now. I want to calculate the pH. Well, let's recall, if I know the hydrogen ion, all I need to do for pH is go negative log n of 0.006, close my parentheses, and then it's 2.22. Okay. Fantastic. So I've check. And then finally, the last thing I'm asking for is what's known as the percent ionization. All right. So the final thing, and I'll scroll this up, is percent ionization. And to do this, you just very simply take the hydrogen ion. All right. So all you're going to do is take the hydrogen ion concentration. You're going to divide it by the original acid. In this case, it's COOH concentration, and you're going to multiply that by 100. So what's that going to look like? That's going to look like this. So you're going to go 0.006 divided by 0.2 times 100. All right, so go ahead and plug that into your calculator. And that gives you 3% ionization. So there are our answers. All right. And just so you know, typically the shortcut, it's fine to use the shortcut as long as you're under about 5% ionization, and we are. All right, so we're good to go. You're always going to be able to use that shortcut though. Okay. All right, so finally, example number 3. Okay. All right. So this is example number 3. A 0.75 molar solution of HX has a pH of 4.5. Find the following: Ka, POH, hydroxide ion, hydrogen ion, and percent ionization. Woo, you've got a lot going on there. All right, you're going to notice I use this HX a lot. That just is kind of a generic weak acid. All right, so remember, HX is going to ionize into H plus X minus. Okay, I've given you the pH. Well, if I give you the pH, it's very easy to come up with these 3. All right, so let's do that first, and then we will go back and deal with the Ka. All right, so if I've given you the pH of 4.5, remember what we're going to do when, well, there's different orders in which we can do this, but let's first, so the pH, I'm just going to rewrite this. pH is 4.5. All right, your POH is going to be just 14 minus 4.5, so that's going to be 9.5. Great. Now, to go from pH to your hydrogen ion, all right, so we are going to, remember, go second log negative 4.5. All right, and that is going to give us our hydrogen ion concentration, and that's 3.16 times 10 to the negative 5th molar. All right, again, I had second log negative what your pH was. To find your hydroxide ion, we're going to do the same thing, but with the POH. So second log negative 9.5, and that gives us 3.16 times 10 to the negative 10th. All right, so there we go, molar. Okay, so great. So I have figured out so far, I have figured out the POH, so we're done, the hydroxide ion and the hydrogen ion. It's now, oh, and I can actually do the percent ionization right now as well. So let's go on ahead and do that. So for my percent ionization, I'm just going to take my 3.16 times 10 to the negative 15. I'm going to divide that by my original 0.75. I'm sorry, 3.16 times 10 to the negative 5th, not 15th. So 3.16 second E negative 5 divided by 0.75 and times 100. And it gives you a really tiny percent, 0.00, about 41% ionized. Okay, so these are all things I was asked for so far. So we'll go look at all those answers I'm giving. All right, all of that information just from what I gave you, but I have not answered for Ka. So now for Ka, be careful, okay, because, all right, make sure you're putting in the right numbers. You know the hydrogen ion. If you know the hydrogen ion, you also know X. They're going to be the exact same thing. Ka is not going to have hydroxide information in it at all. So it's the hydrogen ion, 3.16 times 10 to the negative 5th, and that's squared because hydrogen ion and X are going to be the same thing. Then you're going to put it over 0.75 minus 3.16 times 10 to the negative 5th. Now you may be thinking, wait, you told me I could take this part away in the ice problems. Well, I did if it's a matter of a shortcut in that you don't have to use quadratic equation, but here we can go on ahead and do that. All right, and when you put all of those numbers in, take a moment, make sure we're calculating it correctly. All right, so 3.16 -5 times 3.5. Okay, divided by 0.75 minus 3.1. And you should get your Ka to be about 1.33 times 10 to the -9th. This is a very weak acid. All right, we're going to be doing a lot of practice with this. Hopefully you're getting the hang of using your calculator and being able to find all of this information about our acids. All right, have a great day.